Please welcome a program manager from DARPA's Information Innovation Office, Dr. Jennifer Roberts.
Good morning. This morning I'm going to talk with you about the Synergistic Discovery and Design Program and tell you a story about how this program is enabling us to discover new materials that can potentially unlock lower cost, more efficient solar applications in the future. So first, a little bit about the Synergistic Discovery and Design Program. So this program aims to accelerate design in domains where we don't fully understand the science. So these are domains like biology or certain fields of chemistry where we really don't understand the science well enough to have mathematical predictive models that form the foundation for simulation capabilities. And in general, if you think about design and the way we tend to do design across many domains today, often what we'll do is we'll start by having physics-based models and we'll use them to build simulations that allow us to build all kinds of complex systems, be it the computer that you're hopefully not using right now, your phone, the lights in this building, buildings, trains, planes, automobiles, all of that. But what do we do in these domains where we don't have this simulation capability? And the underlying hypothesis behind the program is that perhaps we can take that modeling and simulation capability and we can replace it with high-fidelity experimental data paired with artificial intelligence algorithms that help us hypothesize new scientific theories directly from that data. And then using that ability to hypothesize new science as we go along, pair that with new types of design algorithms that deal with empirical uncertainty in a very principled way, so that we can ultimately enable robust design in these domains where simulation is currently not possible. So to give you a little bit more flavor for how that might work, I'm going to talk a little bit again about our use case. We want to develop these new types of materials that can unlock lower cost, more efficient solar applications. And let's say I come up with a design for a new material. Well, first I'm going to try and test it out in the lab, see whether I can construct this new material, and chances are that my first experiment is going to fail. Because again, I don't fully understand the science, so most of my experiments are going to fail at the beginning. So what we're going to do is we're going to run this series of experiments and collect information about both those experimental successes and the failures so that we build this repository of experimental information that an AI algorithm can use to predict what might be happening with the underlying science. And it's worth noting that this mix of successes and failures is what can enable an AI approach to really have a chance of hypothesizing something that's real. So then we're going to take this repository of data and pair that with two different types of algorithms and use it to drive the development of two types of algorithms. One type that is learning scientific principles directly from that experimental data, and another type that is moving us quickly toward robust designs that are reproducible across multiple labs. So that at the end of the day, we can put these pieces together, our experimental repository, our scientific discovery algorithm, our design algorithms, and quickly move toward robust applications, toward robust technical results where we've already tested for reproducibility as we go along, and we have an understanding of why the resulting material works, an understanding of the underlying science. So today I'm going to talk a little bit more about a use case in which we've used this type of technique to effectively double the number of Perovskite materials, a certain type of solar material, every 3 months for most of the first year of this program. So Perovskites are a new type of solar material that is the subject of a lot of research and investigation right now because it has the potential to be lower cost and higher efficiency. And what's exciting about this material is it's effectively gone to 27.3% efficiency in 10 years, which is about a quarter of the amount of time that it took for the solar cells on the market today to reach the same level of efficiency. What's also exciting about perovskites is they have the ability to be formed into thin films. So if you think about the application, you could imagine embedding a perovskite film inside of a window and then putting one of these energy-generating windows in every window of an office building, or one window per office, and providing enough power for that whole office building just by giving it the right windows with these perovskite materials embedded inside. So it has the power to be, it has the potential to really unlock solar power at a scale that we don't have today. But there is a problem. If you look at the type of perovskites that are generally studied today, they tend not to be terribly stable or stable enough in a typical environmental condition. So what we're focusing on the program is trying to identify a large number of potential perovskite materials that might have the high efficiency type properties that we're interested in, and also provide us with the type of environmental stability that we would need for a realistic solar application. So during the program, what our teams are working toward is first discovering a large number of new types of perovskite crystals and then screening them to determine which ones have the structural properties, the stability, and the electrical properties that we're interested in. And to give you a flavor of what this looks like, if you focus on the crystal structure in the center of the diagram, that shows the structure associated with a perovskite. And each of those fuchsia balls is a particular type of halide. Inside of the octahedral structure that's formed by those halides, there's a metal, which is depicted by the gray ball. And floating inside, there's an amine, which is essentially the floating molecule that gives the perovskite its structural properties. And this forms a very large search space because we could put different types of molecules and components in each of those different halide, metal, and amine positions. And the question is, how do we search through a potentially very large space in order to create the crystals that have the solar properties that we're interested in? So I'm going to move into some of the AI challenges, but first, before we get there, we need to understand kind of the nature of the experiments, because that's what forms this very large search space that we need to explore in order to get to these solar materials. So to understand this search space, we first need to understand how you might create a perovskite crystal. There's a few steps. So first we take an inorganic, an organic, and an acid, and we mix them together. Then we heat the solution, and then we shake for a variable amount of time. And through this experimental process, there's about 8 different parameters that we can manipulate. We can manipulate the relative concentrations of the precursors, our inorganic or our organic and our acid. We can manipulate how much we heat the solution, how long we shake it, and we can also change the components that lead to that amine, metal, and halide inside the resulting structure. So altogether, these experimental variables create a search space with 10 to the 7th or more than 10 to the 7th different conditions, which is way too many for us to test because we can only currently run about 100 of these experiments per week, which means that if we were to fully search the space, we would take several centuries to search for the solar materials, and we would obviously like to have a solution much more quickly than that. So to expand upon this search space and talk about why this is a hard problem, here we're looking at a small subset of the experimental search space. where on the right, or on your left, you see the parts of the search space that are traditionally well studied, and on your right, you see some of the parts of the search space that our teams are starting to explore now. Now, on each one of these plots, we have 3 different axes. The axes represent the concentration levels of our 3 precursors. And then the title for each one of these 3-dimensional plots essentially determines the amine, that floating molecule that ends up in the middle of the perovskite and gives it its electrical properties. Within each of these diagrams, what we want are red dots, because red dots indicate that we're creating a very large crystal that might be appropriate for solar application. Now, if we look at the methyl ammonium on your left, those are the ones that are very well studied. They're also the ones that have the issues related to environmental stability. But what you notice about that search space is it's very homogeneous. Inside the methyl ammonium space, most of the experiments that you might try are likely to work, which explains why chemists have been spending so much time in that part of the space. If you move to some of the other types of amines, what you'll see is that the space is much more heterogeneous. It's much more difficult for us to predict ahead of time which of these experiments are going to result in a crystal that's large enough for us to investigate further. So effectively, what we have here is a black box optimization problem, where you can see on our y-axis, you can imagine having a crystal quality score, where again, red is high, blue is low. And we really want to optimize so that we are identifying the experiments that give us the largest crystals. And in this plot, our horizontal plane really represents that high-dimensional space of 8 different parameters that we could manipulate. But the problem here is that, again, we have this space with 10 to the 7th combinations. We don't know a whole lot about it ahead of time, and we can really only explore the space at 96 points per week. So the question is, what do? We don't actually know what this space looks like. What type of algorithm can we use to really efficiently converge on areas that give us solid crystals? And the approach that folks have been taking is to build a semi-automated experimental process and augment that with a Bayesian optimization approach. So this is joint work between Fordham University, Haverford College, Lawrence Berkeley National Labs, and the Broad Institute at MIT. And effectively, they've set up an automated pipeline to run the experiments. Then they have a step where it's a semi-manual step to grade the quality of the crystals and provide that information to the algorithms, the Bayesian optimization algorithms, that then suggest the next round of 96 experiments. And the teams have been using this process on a weekly basis to start to probe this space. Now, what the Bayesian optimization algorithm allows us to do is really trade off between exploration of the space and exploiting the knowledge that we've gained along the way. So the Bayesian optimization approach admits that we don't necessarily know a lot about the space that we're trying to optimize over, so we place a prior over our objective function. And then at each experimental cycle, we try and identify the experiments that are most likely to give us the highest information gain. So if we start the video here, what you can see is those error bars around our objective function go down every single time that we make a measurement, and we're using the areas of largest uncertainty to decide what experiments to run when we're really trying to explore the space, and then we can flip over and take advantage of the information that we've gained to focus on parts of the space that have yielded high-quality crystals in the past. Now, Bayesian optimization is a technique that's been around for some time and is broadly applicable. So I'd also like to talk about the work that the team's been doing to take this general approach and tailor it to the chemistry application. And there's been 3 main thrusts to that work. One is hyperparameter tuning that use simulations of the chemical problem in order to decide how to tailor the algorithm. Second, the team worked to map the technique to the discrete constraints that kind of come from the underlying chemistry. Essentially, we can only measure the concentration to a certain level of precision, and in the dialogue back and forth between our experimentalists and our computational group, effectively they increase the precision of the concentrations that they were measuring by 20 times in order to help improve the optimization technique. And then finally, the computational team has worked to restrict the domains so that we've reduced the size of the search space by 62%. I'm going to talk a little bit more about that part of the work. So effectively, if you naively frame the search space, we would search through all possible concentrations of our 3 precursors. But it turns out that not all of those concentrations are physically realizable. So effectively, the teams have identified this fully automated pre-screening process in order to identify which concentrations we can create in the real world. And then from there, the experimentalists provide this point cloud of realistic concentration levels, and the computational performers have embedded a quick call algorithm in order to constrain the search space that's used by the Bayesian optimization algorithm to enable it to much more efficiently find worthwhile experiments. So together, this approach has enabled the teams to increase the number of known materials with an inverse temperature crystallization property from 2 to 14, which again is effectively doubling the number of known materials every 3 months for much of the first year of the program. So to give you a flavor for what this inverse temperature crystallization property is like, you can think of sugar in coffee. So if you have sugar in coffee, it dissolves at a very high temperature and it crystallizes at a low temperature. So making iced coffee without heating it does not work terribly efficiently. This type of material works the opposite way. So it effectively dissolves at a low temperature and it forms crystals at a high temperature. And that type of property makes it so that we can much more easily automate the experimental process because it allows us to use liquid handling robots. So to show you what this looks like, here the video is showing the solution starting at 50 degrees and moving up to 90 degrees Celsius. And what you'll see is those crystals forming as the solution becomes more hot. So again, the teams have very rapidly increased the number of known materials with this property, doubling them every 3 months for the first couple months, first year of the program. And as we've gone through that process, we've effectively generated the largest known repository of Perovskite chemistry data, a resource that we plan to make available to the research community. In addition, what you've heard today is how our teams have created this semi-automated process and paired that with a Bayesian optimization technique to allow us to efficiently search this high-dimensional 10 to the 7th size space in order to discover these 12 new materials. And where we're going in the future is pairing that with the scientific discovery algorithms that will allow us to take advantage of this experimental repository and better predict which of these materials will result in the types of properties we need for low cost, high efficient, and environmentally stable solar applications in the future. Great, so I have a couple questions here. So how is AI used to assess the environmental stability of perovskites in solar cells? Is the mechanism of environmental transformation known? So I think the environmental stability question is something that we will be hitting in the future, right? So there's an experimental piece where effectively we'll be putting the crystals in a chamber with typical humidity conditions that might often cause perovskites to degrade, and then we'll be sensoring that environment to track what happens with the material over time. Then once we have that data will allow us to use the scientific discovery style algorithms to say, okay, what is it in the underlying chemistry, what types of correlations to start, and hopefully what types of chemical principles related to maybe the energy models inside of the material are predictive of different types of environmental stability. Now that's all future work, and we're looking forward to getting there in year 2, 3, and 4 of the program. You mentioned that the program is creating a large experimental database of successes and failures. Could you share more about that? Very happy to do that. So inside the program, we are running these weekly experiments and collecting 96 new data points, new experimental framings per week. And we're uploading that repository to the Texas Advanced Computing Center, which is an NSF-subsidized computing resource. And right now we have about 10 open slots where researchers could use different types of AI techniques to recommend what experiments we might want to run next week. And we have a couple teams on the program that are making these recommendations, but actually there's room to incorporate more techniques, more research groups. So if you are interested in collaborating with us, please come and talk to me. And I think that's all the questions that I have.